We are recording. Yay. Algebra 2, 9.3, Wednesday, January 31st. It's the last day of January. How do y'all feel about that? It feels like January's been like 3 years long, hasn't it? Yeah. All right. Oh, tiny desk. I'll fit. Don't worry. I may not be able to get out, but I'll get in. Uh-oh. Okay. So what we're doing in this section, I'll get rid of the calculator for now. What we're doing in this section is we're going to be graphing rational functions. Now, we have already been graphing rational functions, but we've been graphing the easy variety. What I want you to realize or remember, because we defined it before, a rational function is nothing more than a polynomial over a polynomial. And they're very, very important types of functions. In fact, we study them a lot in pre-cal, okay? And pre-cal, we're going to be doing a lot of what we're doing in this section, but with more exhilarating types of problems. That's honors pre-cal, if you're interested. And, of course, you'll do them in double dual as well. But let's review. This is what we quizzed over yesterday. I want to go through this kind of quickly so we can get to the new stuff. But it's worth going over this as a review. 1 over x is our parent rational function. It's a constant over a linear function. So it still classifies as a rational function. It's the function from which all other parent functions that are linear over linear can be derived. All right. So here we have g of x, and we want to answer these simple questions. You can just lay it on the table, Henry. All right. First thing that I would do here is to put it into transformation form. I would take the 3 that is in the front and just pull it, or in the top, and write it out front. And that gives us then an inside and an outside. So the x minus 5 is the inside, and then the 3 and the minus 9, that's the outside. That's affecting the y values, okay? So that standardizes the form for us. Now, if we list what these transformations do from left to right, what does the 3 do? Vertical stretch by a factor of 3. Do we really show that when we graph it? No, we just know it's 3 times steeper. The next two are muy importante. What does the minus 5 do?
5 right.
5 right or right 5? Now, notice I could drop straight down here. If I move the entire graph right 5, where's the new vertical asymptote at x equals what? 5. It was at 0. Now it's at 5. Cool. Cool. What value am I excluding from the domain if that's where the vertical asymptote is? 5. I'm also excluding 5, which means I can go straight to the set notation for the domain. It's the set of all x such that x is not equal to 5. That's the first time I say not equal to, because the domain is asking what values work. All of them but 5. 5 is the only one that doesn't work, okay? Now, what does the minus 9 do? It moves it down 9. So that changes the horizontal asymptote, which was at 0 to what? Y equals, if we moved it down 9, it's negative 9. So what's the excluded y value? Negative 9. We don't hit the asymptote. So in set notation, the range is the set of all y, such that y is not equal to negative 9. Notice how all of those are intimately related to each other. Now, we can come back and write the interval notation for both of these. The interval notation for the domain is just x epsilon, negative infinity to 5, union 5 to infinity. We step over it. Okay? We step over it like dog poop on a sidewalk, right? Poop on a pavement. For the range, we say y epsilon, negative infinity up to negative 9, step over negative 9 with parentheses, and then cruise to infinity. Okay, there it is. Now, with this information, we can quickly sketch a graph of what this function looks like. So let's draw it over here. I'm going to go to 5 right here and draw a vertical asymptote. And then I'll come down here to negative 9 and draw a horizontal asymptote. Looks like that. And remember, we've created 2 new quadrants, or 4 new quadrants by the 2 asymptotes. And it's either going to live in 1 and 3 by default, or if we reflect it by any amount, x or y axis, it's going to live in 2 and 4. Did we reflect this one? No, there's no negative multiplier, so it has to live in the standard 1 and the standard 3. So there's your graph right there. Quick and easy graph. We'll call it F. There we go. Now, the other thing that we did is we shifted points around. We followed where 1, 1, which is on the parent function, and negative 1, negative 1, which is on the parent function. We mapped where they went. So let's go ahead and do that. We'll do the x's first, both of them at one time, and then we'll do the y's. So remember, for the x, the 1, all we have to do is pay attention to the inside. Do we add 5 or subtract 5 if we're moving it right 5? Good. It's the opposite of what shows. We add 5. So what's 5 plus 1? 6. What's negative 1 plus 5? 4. So there's the two new x values, okay? Now for the y values, we have to do two things. We have to multiply by 3 and subtract 9. So we go times 3 and minus 9. And we have to do it in that order because of your dear Aunt Sally. Multiply first. So what's 1 times 3? 3. What's 3 minus 9? Negative 6. Boom. And we'll do it for negative 1. What's negative 1 times 3? Negative 3. What's negative 3 minus 9? Negative 12. Booyah, we got them. Those are the two new points on the graph. You can even graph it. 6, negative 6 would be right there. And then 4, negative 12 would be somewhere right there. Those are the two new points. Okay, good stuff. That's what we quizzed over yesterday. Hopefully now, if you didn't make 100 on the quiz, this right here sets you straight. Okay, when I hand back the quizzes tomorrow, I don't know if I want to go over them in great detail because I'd rather finish the notes and give you the remaining time to work on your assignment, which is due Friday. Okay, I thought I would finish the notes today by going fast, but there's too much information here, so it's kind of impossible to do. All right, what we're going to be doing in this section is we're going to be graphing things that look more like this, more like f of x equals this, where I have a polynomial over a polynomial. It could be a quadratic over a quadratic. It could be a linear over a quadratic. It could be a quadratic over a cubic, all kinds of different combinations, okay? But what we're going to do is we're going to go through and we're going to collect information. We're going to collect info, and we're going to graph as we go. And graph it as we go. We don't really need a comma there. Graph it as we go. Collect info and graph it as we go. Now, when you quiz or test, this page right here is going to be projected. Okay, that's what Coach Richter said. She's kind of in charge of the Honors Algebra 2. We're revamping it this summer, and next year I'm gonna say that this doesn't get projected to the honor students. So next year's kids, they'll have to know this, right? I'm not going to project it, but for y'all, we'll still project it. Now, this by no means is a flow chart. You don't necessarily go through and find these things in the order in which they're shown. You certainly can try, but there is a natural flow and a natural order to finding these things that I'm going to teach you, and it should kind of make sense. All right. What we're trying to do ultimately is we're trying to come up with the graph of these functions. And we want to avoid doing what we did in Algebra 1. Remember in Algebra 1, when you wanted to see what a graph looked like, you would make a little t-table, and you would have like -2, -1, 0, 1, and 2. You would pick random values of x, and then you'd plug them in, and you'd find the y values, and then you'd have these ordered pairs, and then you would just connect the dots. Remember doing that? That's a very primitive way to sketch a graph. It still works. By all means, pick any values you want, find the y values, plot the points, and connect the dots. But it's very primitive, okay? We don't want to be primitive anymore. We're Honors Algebra 2 students, so we want to graph it judiciously. We want to see if we could sketch this graph with as little information as possible, okay? So the first thing that you're going to do, number one, out of the box, for any type of function, is you're going to factor it. Okay, you're going to factor it for the purpose of finding the domain. To find the domain. We want to find the domain, and it's easier to do once it's factored. You want to be talking about the graph where the graph doesn't exist. That'd be kind of bad if you're talking about the graph and the graph doesn't even exist there, right? You go to the concert, like, hey, there's no concert here. Oh, that's kind of silly of me. I should have checked to see if there was a concert here before I came to the concert, right? You check the date, you see where the concert is, and then you go to that spot. Now you're at the concert and having a good time. All right, so once we factor it then, the whole point of factoring is to find the domain. The next thing that shows up that is related to the domain are these two right here. I would have written these side by side at the top. This is the second thing that we're going to do. We're going to check to see any value that makes the denominator 0. Any value that makes the denominator 0. It's either going to be a vertical asymptote, like we're used to, or it's going to be this new thing called a hole, okay? I'll show you what a hole is on the second example. Once I have those two, I'll have my vertical asymptotes and any possible holes in the graph identified. Now I want to pick a couple of points. I don't want to make a T-chart out of the blue. Yeah, I put your stuff on the chair right there, okay? I don't want to pick random points, but I do want to pick 2 points that are very, very important. So these two right here are the next thing that I want to do. I want to find the x-intercepts, and I want to find the y-intercepts. Okay, that's the next thing that I do. Once I do that, this is what I do last. The last thing that I do is I find my horizontal asymptotes, and I'm going to just briefly mention today a slant or an oblique asymptote. So we got our HAs and our SAs. That's the last thing we do. Actually, it's the second to last thing to do. Instead of saying last, let's change that to the fourth thing. We'll change it to the fourth thing. And then the last thing that we do, ultimately, the last thing we do, if we can, is we find the range. And we get the range exclusively from the graph. So our task is to graph it. We want to sketch a graph. Once we have the graph, we'll find the range. Okay? Let's try it out on example 1 down here. Example A. Identify all the information. Now, you're not only going to be given this right here, which tells you what to do to find the information. The order's a little wrong from what I'm teaching you, but it's all there. You're also going to be given stuff like this. You're going to be asked to find stuff. You're going to be given the names of the things that you're trying to collect in order to complete that graph on the right-hand side. All right, so let's meet this. We got a quadratic over a quadratic, okay? I got an x squared over an x squared. This is not just a transformation of 1 over x, but it is a polynomial over polynomial. It's a rational function. What's the first thing we do once we size it up? We do what? Factor it. Okay, so when I factor this, I need to factor using the numerator and factor doing the denominator. So one at a time. What's the first rule of factoring? Look for a greatest common factor. In the top, we do have a GCF. What is it? X. So if I factor out the x, I'm left with 3x plus 1. That's factored completely. In the bottom, there's no common factor, but I have a difference of squares. So that factors into the product of two whatchages? Conjugates. Y'all remembered. Good. So the square root of x squared is x. That goes in the front. The square root of 9 is 3. That goes in the back. All right. So from here, when it's factored, here's what we do. We factor so that we can find the domain. Here's how we're going to find the domain. Just like on our parent function up above, what value of x was not in the domain? 5. Why didn't 5 work? Because it made the denominator 0. Yeah? It made the denominator 0. So here's what we're going to do over here. We're going to basically set our denominator equal to 0. So I'm going to get x plus 3 times x minus 3 equals 0. Now, you can either set them both equal to 0, or please tell me at this point you can rattle off the roots. If x plus 3 is the factor, what's the root? X equals negative 3. And if x minus 3 is the factor, what's the root? 3. Yeah. Or you can set them both equal to 0. I don't care. Set them both equal to 0 and subtract 3 and add 3, and you get the same two roots. Now, these are important values because these two are not in the domain. They're the only two. Okay? They cause a 0 in the denominator. They cause a 0 in the denominator. So we're going to jump down here. The first thing we fill out on this piece of information chart is the domain. It's the set of all x such that now x is not equal to plus or minus 3. Oops, not a parentheses, a brace. And you can list them like that, plus or minus 3. But we do say not equals here. We don't put equals here because the domain is saying which guys work. And now we're saying, hey, these are the only two that don't work, and therefore all the other values are fair game. Now, the next thing that naturally flows from finding the domain is this. If we can't divide by 0, then what's going on at 3 and negative 3? Those are called discontinuities. They interrupt the flow of the graph. The graph lives to the left of negative 3 and to the right of negative 3, but not at negative 3. So the graph is discontinued there. The graph lives to the left of 3 and to the right of 3, but not at 3. The graph is discontinued there. Your discontinuities are going to be one of two types. Let's come up here. Your discontinuities are either going to be vertical asymptotes, okay, or removable discontinuities, which are called holes. You could just call them holes if you want. Now, you don't have a lot of experience with vertical asymptotes, but you have even less with holes. Here's how you can tell there's going to be a hole. Okay, there's two ways to tell. First of all, let's talk about what a hole is. We know what a vertical asymptote is, right? A vertical asymptote shoots your y values to infinity or negative infinity. It shoots them straight up, skyrockets them to infinity or down to negative infinity. Here's what a hole is. Imagine you have a graph just looking like that, just minding his own business. And out of the blue, here comes Swiper from Dora the Explorer, and he swipes away a point. We didn't yell loud enough. He swiped away a point, okay? Leaving a what in the graph? A hole, right? Now, it's only a point that's missing. A point is infinitely small. We don't draw it to scale, all right? In fact, what we do to accentuate that there is an ordered pair missing, we draw an open circle around it. This is a point is missing. This is called a hole or a removable point discontinuity. If I knew the coordinate of that hole, I could plug that hole and make it continuous there again, all right? This occurs when you have the following. Let's say you had an x minus a factor in the top, and then you had other factors, whatever. They could be anything. And in the bottom, you had the same factor, x minus a again. When you have the same factor in the top and bottom, what can we do with those factors if they're both in the top and bottom? Not cancel them, but we can divide them out. We can divide them out. Or you could say this. We can remove them from the equation. That's another way to say it. It's generic, but it's not cancel. They either divide out, leaving a 1, or you could say we remove it from the equation. If you can remove that factor from the equation, then this function is going to have a hole at a comma question mark. All right? It's not a vertical asymptote. It's just a hole. There's just a little piece of the graph missing. All right? The other way to know there's a hole is this. This is how we do it in pre-cal. If you plug in a value like a and you get a 0 in the top because of the x minus a factor and a 0 in the bottom, that's another way to tell that you have a hole. Here's an easy way to remember 0 over 0 means a hole. You write h and l and e on the other end, and now you have not just a hole, but you have a hole. Okay, you can fall into the hole if you're not careful. Right? Fall in the manhole. There's a hole if it causes a 0 in the top and the bottom. If it causes a 0 in the top and the bottom, that means there's a factor of x minus that number in the top and bottom that can be removed. And of course, by comparing that now to a vertical asymptote is when only the denominator equals 0. So you have something like whatever, ... over x minus a. Okay? You cannot remove it. You cannot remove it. Now we're going to have a VA at x equals a. It's not an ordered pair. It's a vertical line, so it doesn't have a y value associated with it. I'll show you in the next example how we find the y value of the hole. For now, just know there's a hole at x equals a. There is a y value that goes along with it. Here it's just x equals a. Now, here's how you can remember it. Non-zero over 0 means vertical asymptote. That's how we remember it in pre-cal. It's an easy way. Any value that makes the denominator 0 but not the top is going to be a VA. Any value that makes both the top and the bottom 0, that's going to be a hole. All right, so there's your introduction to them. Let's come back down to our example here. The two factors I have in the denominator are x plus 3 and x minus 3. My question to you is simple. Do either one of those factors divide out with a similar factor in the top? Do I have an x plus 3 or an x minus 3 factor in the top? No, I do not. Okay, so neither one of these are removable. These are not removable, which means they must be what? Not holes, but what? They're VAs. Yeah, they're vertical asymptotes. So if we come down here to the vertical asymptotes, this would be the second thing that we would do because it's intimately related, and this is also the second thing we do. It's intimately related to the domain. We have vertical asymptotes at x equals -3 and x equals +3. I would ask that you list those separately because we're not just listing x values, we're listing equations. X equals -3 is one equation, x equals +3 is the other. Now, do we have any holes? Are there any holes here if nothing divided out? No, so we'll say none. Okay, we'll introduce that problem on the next rational function that we encounter. So this one doesn't have any holes. They're both VAs. Now, what we're going to do once we find their VAs is we're going to sketch them. All right, we're going to sketch them. Oops, I didn't even spell sketch right. Let me try that again. Sketch them. All right, so we come over here. We sketch it as we find it. -3 looks like this. +3 looks like this. It's the vertical asymptote. so on and so forth. There we go. Okay. Now notice what we've done. We've split this up horizontally into 3 sections instead of just 2, like on our parent function 1 over x. We have the graph to the left of -3, we have the graph to the right of 3, and then we have this interesting section between -3 and 3. Something cool's happening there. I don't know what just yet. We don't have enough information. Okay, so what do we do next after we find the discontinuities? Well, we don't want to make a table of values like this. We don't want to get all crazy and pick random values to find points. But there are 2 points that are worth finding each and every time. And that's these 2 guys right here. Okay, so this would be the 3rd thing that we find. The x-intercepts and the y-intercepts. All right, so how do we find the x-intercepts? We set the numerator equal to 0. And how do we find the y-intercepts? We set the x equal to 0. Okay, so let's come back here to our equation. This is after you get rid of any holes. Okay, you set the numerator equal to 0 after the holes are gone. I'm going to say after the holes are gone. It doesn't apply to this one because there are no holes. All right, so now if we look at the numerator, we have 2 factors in the numerator, don't we? We have x and 3x plus 1. So now for the x-intercepts, I'll do the work right here. We really want to set the whole thing equal to 0. But the whole thing is equal to 0 when just the numerator is 0. So that's going to be x times 3x plus 1 equals 0. We already set the denominator equal to 0. Those are your discontinuities. Those are your values that aren't in the domain. They're both VAs here. And now we set the numerator equal to 0, and that gives you the x-intercepts. Now, if you can just look at those 2 factors and rattle off the roots, that's great. If x is a factor, what's the corresponding root? 0. And do this one in your head maybe. If 3x plus 1 is the factor, what's the corresponding root? Not 1/3, but -1/3. Now, if you need to show intermediate steps, go for it. Set x equal to 0, set 3x plus 1 equal to 0, and then solve, right? Solve. You would subtract 1 and divide through by 3. But we get these 2 fellows right here. Now, because they're x-intercepts, these are actually points on the graph. So I would recommend writing them like this: 0, 0, and -1/3, 0. -1/3, 0. I'm just going to copy this right here, and I'm going to paste it over here to x-intercepts. Boom, there they are. I did my work off to the side. Now, once we have 2 points, can't we plot them? Bless you. So as soon as you find them, sketch them. Sketch them as you find them. All right, let's plot the 2 points. 0, 0, that's the origin. And -1/3, 0. Ay caramba. -1/3 is just to the right of 0, isn't it? It's almost too hard to draw it to scale, or those 2 points will be touching as I draw them. Ooh, gross, right? So I'm going to draw a little bit closer to -1. But realize it's actually closer than that, okay? But it's in the right spot. It's between -1 and 0. Those are my only 2 x-intercepts that I have. Okay, what's next? Well, we find the y-intercepts. All we got to do is let x equal 0, which means we're going to, I would say, plug into the original. This is where plugging into the original is going to be faster than plugging into the factored version. So if I come up here, here's my original version. I'm just going to say f of 0. F of 0. That's plugging into 0 for x, right? Now, the reason you want to plug into the original is because of this. Every term that has an x in it, when you plug in a 0, becomes 0. So in the top, I get 0 plus 0, which is 0. And in the bottom, I get 0 minus 9, which is -9. And of course, what's 0 divided by -9? 0, yeah. 0 divided by any non-zero number is 0. Now, that gives me another point, doesn't it? That means that the y-intercept is the point 0, 0. So I can sketch it. Now, if I go to 0, 0 to sketch the y-intercept, what do I notice? I already have it. Uh-oh. The y-intercept was also an x-intercept. So I don't get a new point to sketch here, unfortunately. But at this point, it could have been different. Here's the deal. If you ever have a y-intercept, you're going to have only one. No more than one. There can only be one y-intercept. But you can have multiple x-intercepts. We have 2, okay? One of them happens to be the y-intercept. All right. Now, once we get done with that information, the fourth thing that we find is this, the HA or the SA. We know what HA stands for, right? Horizontal asymptote. Guess what SA stands for? Close, not symmetrical, but slant asymptote. Slant asymptote. Here's what a slant asymptote would look like. Let's say you have a vertical asymptote right here. Instead of being horizontal, the asymptote is a slanted line, okay, with the slope. It's going to be of the form y equals mx plus b. It'll be the equation of a line. And what the graph does is it might come from the vertical asymptote, and then it'll go to infinity as it goes out to the right. Or it may be something like this. It may go down to negative infinity as it goes out to the left. But as it does so, it's getting closer and closer and closer to becoming the equation of the line. In other words, it's using the line on the right as the stairway to heaven, and it's using the slant asymptote on the left as the highway to hell. If you like classic rock references. Stairway to heaven on the right, highway to hell on the left. What two bands are those, do you know? Very good. Led Zeppelin and AC/DC. Very good. Okay. Now, the good news is you're not going to be responsible for slant asymptotes in honors algebra 2. Just be aware that they exist. That's something that we explore in greater detail in pre-cal. You're responsible for horizontal asymptotes that can occur one of two ways. All right. So let's talk about slant asymptotes so we can dismiss them. Slant asymptotes come from analyzing the end behavior of a function. That's what the HA and the oblique slant asymptote are. If the degree of the top is bigger than the degree of the bottom, what that means is it means the top grows faster. If the top has a larger degree, you're going to have possibly a slant asymptote. Okay? You don't have to worry about that. Is that what we have in our situation? What's the degree of our numerator? 2. What's the degree of our denominator? 2. Is the top bigger than the bottom degree-wise? No. If the top had been a cubed, now we're going to have a slant asymptote. Okay? If the top were bigger, it's going to go to infinity. Okay? Along that line. Here's how you can tell real quickly. I want to make this obvious to you. Let's say that you have both the top and the bottom getting bigger. Let's make 4 little ratios here. But now the top is getting bigger faster than the bottom. So the bottom is growing 1, 2, 3, 4. See that? The bottom is getting bigger 1, 2, 3, 4. But now the top, let's let the top get bigger a little bit faster. 10, 100, 1,000, 10,000. What's happening to those ratios? Are they getting smaller?
Yeah.
Really?
No, they're staying.
The first one's 10. The second one is 50. The next one's 333. 10,000 divided by 4 is 2,500. What's happening to those values? Oh, they're getting bigger. They're getting bigger. They're going to infinity. Anytime you have a ratio and the top grows faster than the bottom, your ratios are getting infinitely large. They're going to infinity. Now, how are they going to infinity? They're following the stairway to heaven, or they could be going to negative infinity following the highway to hell. Okay? That's going to happen anytime the top is bigger than the bottom. Once again, is that our case with our problem that we have? No. Okay, so there's 2 other cases. Let's go back to the top here. If the bottom is bigger than the top, now if the bottom grows faster, let's see what's happening here. You're going to have something like, let's give ourselves 4 ratios, but now let's have the top getting bigger very slowly. 1, 2, 3, 4 in the top. And now let's have the bottom getting bigger. 10, 100, 10,000, 10,000. What's happening to these ratios? These are getting smaller. Remember, I made the analogy earlier in the year about drinking pee in the water? Would you drink a mixture if it was 1 part pee to 10 parts water? Not for me. How about 2 parts pee to 100 parts water, though? Still no for me. But what if it was 4 parts pee to 10,000 parts water? Maybe. If I'm thirsty, I'm saying, yeah, give it to me. I'm thirsty. But what if it were what if it were 5 parts pee to a gazillion parts water? Are we going to even notice that there's pee in it? No, because that's already what's happening with your bottled water with microplastics, right? It's like 1 part microplastics to like a billion parts water, but it's in there and we don't even taste it. So it's approaching practically what? Zero, okay? So anytime your bottom grows faster, that means it's a larger degree. You're always going to have a horizontal asymptote always at y equals 0. Always. The x-axis. Always. Okay? It doesn't matter how much bigger the bottom is degree-wise as long as it's bigger. Is that the case we have with our function here? No. Alas, they're the same degree. So that's not what's going to happen with us. So that gives us the third and final scenario here. What if they grow at the same rate? What if the degree of the top is equal to the degree of the bottom? Well, let's see. If I gave you an example of 5x cubed plus something all over 1x cubed plus something, those were your leading terms. When we're going to infinity, which is the end behavior, we don't care about anything but the leading terms because everything else is small by comparison. If I asked you just to simplify your leading terms, what would you do with the x cubes? Bye-bye. You would divide them out. And what would we be left with? 5 over 1, which is what? 5. Okay? Guess what? That's the case that we have right here, right? If I ask you to simplify our leading terms, 3x squared over 1x squared, what would happen with the x squareds? Bye-bye. And what are we left with? 3. Okay? So anytime they're the same degree, you're going to have a horizontal asymptote at y equals the leading coefficient over the leading coefficient. Y equals the leading coefficient, leading coefficient. So you're not going to have to worry about an essay, but we have a horizontal asymptote now at y equals what? 3. And guess what we're going to do now? We're going to, well, what did you say? Rain? Rain. Oh, not yet. We don't have the full graph. We're going to sketch it as we find it. So we're going to sketch it. So we're going to go up here to 3, and we're going to sketch this little horizontal asymptote. All right. Now we're kind of out of data. There's nothing left to find from that table. Now that doesn't mean that we can't still find information. Remember, we can always resort back to this primitive method, can't we? If you feel like you need more data points to connect the graph, make yourself a t-chart, pick random values of x, plug it in, find the y, plot your points, and you're good. But let's see if we can figure out what the graph looks like from the information that we currently have. All right? Now, notice we divide it into 3 places. To the left of -3, between -3 and 3, and to the right of +3. The easier of the 2 places to graph it are outside of the vertical asymptotes, to the left of -3 and to the right of 3. Because here's what's going to happen. The graph is going to exist in one of 2 ways. It's either going to live up here, or it's going to live down here. One or the other. It can't live in both, can it? Because then it fails the vertical line test. It's going to be very predictable. Now, I would argue that we already have enough information to determine if it lives above or below. So you tell me, does it live above or below the horizontal asymptote? Below. Let's think about below. If it were to live below, we would have found a what for sure? An x-intercept. We would have found an x-intercept when we set the numerator equal to 0. That was to the left of -3. Did we find an x-intercept to the left of -3? We did not. We only found 2 x-intercepts, didn't we? At -1/3 and 0. So if there are no x-intercepts out there, can it live below? Nope. By default, it must live above. By default, it has to live above. There is no x-intercept. Now, by the exact same argument, on the right-hand side, it must also live above. Now, the middle is a little bit trickier. The dotted horizontal asymptote does not apply to the graph between -3 and 3 because that's not the end of the graph. There's 2 options we have here. The graph can either come from -infinity, pass through that point, turn around somewhere, and go back down towards infinity. It can look like that. Or it could do this. It could come from this asymptote, pass through that point, hit a local min, and pass back up like that. It's going to be one of those 2. That's it. Do we know which one of those it is based on our information that we've already found? You think it's the one that goes up? I'll come back to you, Alexa. Why do you think it's the one that goes up? What information that we've already found tells us it goes up?
Well, I'm talking about like the one on the bottom.
Wait, the one on the bottom goes down.
Yeah, but I'm in like the peak. It peaks up.
Oh, so you say it opens down. You think it's the green. Why do you think it's the green and not the blue?
Because on the other asymptotes, it was the in,
Are you saying based on past experience? You can't go based on past experience because what? You've never seen this guy before, and he can just change on you when you least expect it. Okay? We have to go on the information that we have found currently. There is currently, not to my knowledge, any indication that it opens down in the green, but Alexa, you might find something. What do you think? Okay, the horizontal asymptote cuts right across -3 to 3. Unfortunately, our graph is not affected by the horizontal asymptote because that's an end behavior asymptote, and that's only when we go to infinity or negative infinity. So you can actually erase the horizontal asymptote there. In other words, we can cross the horizontal asymptote. That's what you're thinking? Yeah, and that's a very good analogy. You based upon what we previously done, we can't cross horizontal asymptotes. But guess what? This horizontal asymptote doesn't even have to be there because that's not the end of the graph. So we can go ahead and open up and grow right through where the horizontal asymptote was. That's a very good thing to think about. Now knowing that it can cross the horizontal asymptote, we're kind of left with not knowing if it opens up or down. So here's what we can do. I don't want to create a T-chart and just pick random values of x and plot them and connect the dots. But we can be very judicious in the values of x that we choose, right? If I knew the y value somewhere between -3 and 3, other than at -1/3 and 0, wouldn't that be enough to tell me if it opens up or down? I just need one y value between -3 and 3. I have some candidates here, right? I have some nice integer candidates that I can use to find the y value at. I can find the y value at -2, the y value at -1, the y value at 1, and the y value at 2. Which of those four integers is probably the easiest to use? 1. I like it. Okay, so here's what I'm going to do. I have deliberately chosen to find the y value at 1. So I'm going to come up here like we did for the y-intercept. Let's get rid of this because I got rid of this. There we go. Now I can see it. Let's find f of 1. Let's just plug it into the original version, which is easier. When I plug it into the top, what do I get when I plug a 1 into the top? I get 3 1 squared plus 1. That's 3 plus 1. All over the bottom, 1 squared minus 9, which is 1 minus 9. That's 4 over -8, which simplifies to -1/2. Now, what is important about that number? The fact that it is a fraction, the fact that it's negative, or the fact that it's blue? The fact that it's negative. Very good. That's a negative number. So if I come over here at 1, it has to be a negative number. So which one does it have to be, the blue or the green? It has to be the green. It has to be the green. Okay, so now we know that it does, in fact, oops, I want to write it in green. There we go. We know that it does open down. So this is not correct. We can get rid of the blue one. And now it opens down. And I might actually redraw it opening down because remember, it was 1/2. So it's gonna look something like this. It comes in actually a little bit shallower. And then, oops, I couldn't draw it. It comes in like this, passes through there, hits the local max, and then comes back down and does that. There we go. There we go. Congratulations, you just sketched your first rational function. Now, the last thing we do is we find the range from the graph. Now, the range is going to be a little bit difficult, I think, without a calculator. Here's why. I'm pretty sure that I get all the y values greater than 3. Would you agree? I get all the y values bigger than 3. In fact, I get all of those twice. I also can see here that I get all of the negative y values. Would you agree to that? I get all the negative y values. But I also get a tiny, tiny little range right here between the x-axis and whatever this high point is right there. I don't know what this high point is right there. I don't know what the y value is. But I do know that I'm going to get all the y values less than or equal to that y value. So how do we find that local maximum? Well, there's two ways. You either find it using calculus, which many of y'all will end up there in 2 years, right? Take honors algebra 2 next year, or pre-cal, or double dual, and you end up in calculus. We can find it without a calculator, or today we use a calculator. So let me go to the Minnesota link here, and we'll pull up the notability, and we'll go to the calculator. We didn't need the calculator up to now, but now we need it. So you can load the Minnesota, or you go to your yellow one, whatever the case may be, and we go to y equals, and we type it in. We're going to type in the original function. The first thing we do is hit alpha x. Alpha x gets us to the horizontal division bar. Now we type in 3x squared plus x in the top, and x squared minus 9 in the bottom. And we click to the right, and we just double check, triple check that we typed it in correctly. How does it look to y'all? Looks good. Now, we don't hit graph. We always hit zoom 6. Zoom 6 is your standard viewing window. Negative 10 to 10 on both axes. Does that look similar to our graph? Yeah. Whose is prettier? Say ours. Yeah, ours. Very good. You got ours. Very good. Ours. Now, if you were to just look at this graph and you were to find the local maximum, you might think, without knowing what we know now, you might think it just bounces off the x-axis. It has a double root there, does it? Does our graph actually bounce there? No, it shoots across barely by a little and then comes back down. I need to zoom in on that feature right there. I need to zoom in on that feature. So what I need to do is zoom in right here. So go to your window. Don't use the zoom feature. Let's manually do it. For my x-min, x-max, I could go from -1 to 1. Would you agree? Okay, so that's gonna take me between -1 and 1. That's where all my action's happening, right? So x min -1, y max +1. Now, here's what we really want to do for the y's. We want to really stretch this out vertically, big time, because -10 to 10 looks like it bounces. Here's what I'm going to do. For my y min, I'm going to go -0.01. I'm going small. That's 1/100th. It used to be 10. I'm going 1/100th. And then for the y max, I'm going to 0.01. So it keeps it symmetric. Now I can see the maximum. See that? I zoomed in on it manually. So now I can hit second trace number what? Second trace number for the maximum is 4. So it's going to ask me for my left bound. You're not going to have to do this on the homework. Mr. Coach Richter said yours are going to bounce like it's 0. But this is good to do anyway. This is using the calculator to its maximum capacity. That y value is 0.009. No wonder we couldn't see it. It barely crossed by 1,000th. 0.009 is the high point. So what do we know about the range now? For the range, we could say it's the set of all y's such that, let's say y is greater than 3. Let's get that out of the way. Comma, y is less than or equal to 0.009. Ay caramba. Strictly greater than 3, where the horizontal asymptote is, but less than or equal to the local maximum, which is at 0.009. And that's all we have time for today, isn't it?
We have a minute left.
Oh yeah, that's it. We've answered the question. We've answered everything. We've graphed it, and that's it. Tomorrow, I'll give you your quizzes back, and we'll do letter B. Okay? Letter B is going to have a hole in it, and you're going to like letter B. All right.
Are we gonna have problems like this on our like?
Yes, but they'll be a little bit easier than this. You're not going to have to zoom in, but everything else is fair game. Yeah. So practice on the homework.